So now we are going to be solving this problem 912 from the textbook, and we'll solve it in SymPy in Python. So first thing, as you can see, I already saved this file as a Python file. So the first thing we do is that we import SymPy, and as usually we will call it SP. Then we need to define all the variables and parameters and constants that we have in our problem. This we do here. We define them as symbols and we name them like this. And then we define the function, the unknown function, as a symbol as well. Telling SymPy that it is indeed a function. Like that. And then we're ready to define our differential equation. I'll use the equation command to do that, EQ. On the left hand side we have Q plus U times A times T air minus T of T. That's our function here. And then we have plus W times C times Tn minus T of T. That was the left hand side. On the right hand side we have M times C times the derivative of the temperature with respect to time. So I hope I got everything right here. We like some initial conditions as well. I'll call them initial conditions, and we define them as a dictionary. T of 0 is supposed to be T start. I'm not going to put in a number here because I want a purely symbolic solution. Then we're ready to solve it. Desolve the equation, the unknown function, and the initial condition. And I'll call the solution solution. Like that. Let's make a print of it. Like that. Let's see if that works. The computer is thinking. There we have it. It's a little hard to see if that's the correct solution, but if we wrote the right equation here, I believe it is. One way to check it is to make a plot of it, so let's do that. In order to make a plot, we need to define the values of these parameters, so I'll make a list of all the values. W is 2, M is 20, T air is 20, and so on. Like that. And notice I didn't put T start in here. I have to do that in a different way. I'll do that by addressing that element of the dictionary up here and set it equal to 30. That's how that works. You can't substitute numbers into a dictionary like this. Right, so now we're ready to find the solution with values, with numbers. So we'll use the desolve command again, and this time we'll solve the DEQN, but I'll substitute the parameters into the equation, still looking for capital T of t, and the initial conditions are still the initial conditions, but now we've inserted 30 in t0's value here, like that. And let's call that solution num, or whatever you want to call it, and let's look at it like this. And I think I'll just skip this step here because it's a little bit time consuming, like that. Let's look at it. Oh, I skipped one too many. That was a spelling mistake. Initial conditions, right. Let's try again. There we have our solution with numbers in it. And such a solution we're able to print, so I'll try the SP plot. And what I want to print is the solution num, and only the right hand side, because if you see here, the solution num is actually an equation with t, capital T of t on the left hand side and this expression on the right hand side. And it's only the right hand side that I want to plot. In fact, it's the only one I can plot, so I'll choose t running from 0 to, let's say, 15. If you remember from the previous video, the time constant of this system turned out to be roughly 3 minutes, and I know that in 5 time constants time, it should be very close to the new steady state value. So 15 minutes should be sufficient in order to make the system find a new level. Yeah, so let's look at that. There we have the solution, and there we have the plot. And as you can see, it seems to be flattening out here. It's almost at 23 degrees, which is a new steady state temperature. Now, in the problem, we were supposed to find out when the temperature reached 25 degrees. So we need to solve an equation. Actually, what we want to do is to solve this equation here, solution num equals 25. That's kind of what we want to solve. So, in Python, we pull everything over to the left-hand side. So we want to solve this expression, assuming it's 0. The problem is the solve function doesn't do a very good job at this. So I'd like to use another solve function called fsolve, which is a part of the SciPy package. So what I need to do is to load that command from SciPy optimize. I import fsolve. So this is another package called SciPy, and we have a sub package called optimize, and in that sub package we have the fsolve command, which I'm then importing. So now I can fsolve this solution. Problem is, the solution num is a SciPy expression, and this SciPy command won't understand the SciPy command. So what I need to do is to transform this SciPy expression into a NumPy expression. I'll do that using a command called lambdify, like this. Lambdify, this is a command that transforms a SciPy expression into a NumPy expression. All it needs to know is what is the variable, that's t, and what package should I translate into. Well, that's NumPy in this case. So this lambdify command takes our SciPy expression and transforms it into a NumPy expression in terms of the variable t. Right. And then the fsolve command can work with that expression. We just need to add another parameter here, and that's the starting value at which the solve command should begin its search for a solution. So this is a numerical solver, so it needs a starting point. I'm choosing 0. I know the solution is somewhere around 3 or 4 minutes, but 0 is a fine place to start looking for solutions. But don't put in 10 billion or something like that. That's probably going to cause problems. So the fsolve command will return the solution, or in fact it will return a list of solutions. I'll call this list, well, I'm not interested in a list of solutions, I'm interested in one solution, so I'll just choose the first element of this list here. And that I will call T25 because it's the time at which the system reaches 25 degrees. A little technical here, I'm sorry. So we'll make a print of that. I'll write the tank contents reach 25 degrees at time t equals, and we'll input T25 here. Like that. Let's take a look at it. That's the plot. We can see we expect the solution to be somewhere around 3.7 or something like that. Oh, there was a problem there. Need to clarify what that is. I believe the problem is I forgot to put right-hand side on the solution here. Maybe you remembered. I'll try again. .64 minutes it takes. Right. And that concludes our work with the problem 912.